Welcome to the second talk of the SRIP lecture series. This is going to be about the construction that we did in past 4-5 years and planned at IIT Gandhinagar. So the buildings that you see in the hostel area, and some of you might have been to the faculty housing area, they might appear very similar to the regular buildings that you see. But the fact of the matter is that we do not have the design codes in India yet, as of today, to design these kind of buildings. So clearly we had to collaborate with people within India who are expert on the subject and outside India who are experts on the subject. A lot of state-of-the-art knowledge was incorporated in practice, and this is the largest scale implementation in India. So Professor Svetlana Brzev has been involved in the design and construction of this campus since the very beginning, since the planning stage. And she has been a faculty member at British Columbia Institute of Technology. She has retired since and has been a visiting professor at IIT Gandhinagar. She works in the area of earthquake engineering, confined masonry, and so on. So I would like to invite Professor Svetlana Brzev to deliver the second talk of the SRIP lecture series.
Thank you, Professor Kumar. It's a pleasure. Welcome to all of you who are outsiders to IIT GN. I know that there are students from India, from other universities, and also from outside India. So I hope that you're going to enjoy the talk. It's not only about construction, it's about introduction of a new technology, like an example of this construction. So I'm obviously a civil structural engineer. Any civil engineering students in the classroom? Good, quite a few, good. I know that it is a mix of all disciplines, so I hope I made this talk such that it should be of interest to others, not only to civil engineering students. So what I'll be talking within the next, I believe, 40 minutes maximum is about IIT GN's story of implementation of a new technology in a specific country. And I'll explain the technology and research behind that technology. So the topics include what is confined masonry. How many of you have heard about confined masonry in general? Very few. Yeah, that is the technology that is common in some parts of the world, but it is not common at all in some others. So how confined masonry was introduced in India, about campus project, the background and construction, challenges, of course, and then implementation at IIT GN. These two are combined, and then some research that has been going on since the last few years at IIT GN and in India, and I mentioned other countries, but focuses on what has been done here. So what is confined masonry technology? What is, I will use the CM term just to make it short in future. So it is obviously masonry. How many of you are familiar with masonry in the sense that you got some background, educational background on masonry design? Some of you? Okay, that's good. Yeah, masonry as a topic, masonry design as a topic, subject is not very common at civil engineering universities in many places in the world, including India, unfortunately, even though most of Indian housing and building stock is built out of masonry for many centuries, and even now, if you look at the statistics. So, confined masonry is a technology which is different from the common construction practice in India, and most common of modern construction practice in India, and that is to build reinforced concrete frames. So it is, you can see that all around if you go in Ahmedabad or around for the students who are not from India. So they have frames, and after frames you can place walls which are made of masonry, but there we call them infill walls. So they could be blocks. Nowadays you can see lots of blocks, but bricks are most common and have been most common for many years, and so on. However, in that technology, columns or concrete construction is done first, and then after that, these walls are placed wherever they're needed based on architectural planning and so on. However, in confined masonry, walls are constructed first, but there are reinforced concrete elements which look very much like those elements in the frame, which are constructed subsequently, so that walls and these concrete elements work together, and it is a composite system. But it is a wall system. It is not a frame system. So that means something to civil engineering students, obviously. So anyways, as I said, that once completed, confined masonry building looks similar. So I'll show you difference in construction sequence. This is that frame construction. So frame was built already, and then you build the walls as it is. So this is just an animation. And for confined masonry construction, first there is foundation, then there are these reinforcement for reinforcing elements, reinforced concrete elements, and the beam at the base, which we call plinth beam or plinth band, and then there are masonry elements, masonry walls are constructed, and subsequently these walls are constructed. So there is difference in construction sequence, but more importantly, there is difference in behavior. So this results in a completely different behavior, even though systems look very similar. So it's very deceiving to, you have to be an expert or to look at certain features, and the building has to be unplastered, which is not the case with buildings here. So you wouldn't be able to recognize, let's say, buildings on campus, which are confined masonry, are actually confined masonry. So even I wouldn't be able to tell without knowing that right now. So, so here are some characteristic differences. Basically, as I said, in concrete frame, which is shown on the left vertical side, frame, these concrete elements are much larger because they're the main elements. So if you remove walls, frame should stand on its own, both under gravity loading, put them here. Both under gravity loading, which means due to self-weight and all that, and then due to lateral loading, such as wind and earthquakes. However, in confined masonry, these reinforcing elements are much smaller, but they work integrally with the wall. So they're basically like a form of reinforcement to the wall. So maybe the term confined masonry is a little bit deceiving, but confinement in this sense means that there are these elements all around the masonry walls. So that is confinement. Word confinement can be used in different contexts, even in civil engineering. And as a result, at the bottom slide, I'm not sure if that could be seen, at the bottom, no, I can't use it, I'll use the mouse. So this reinforced concrete frame works like a frame. You can see this bending in columns and beams, and then the infill is working just like a strut. And whereas in confined masonry, it all works together like a load-bearing wall. It all moves together. That's the idea. And I will explain a little bit how that happens on examples of drawings of construction features. So you can see here key features of confined masonry buildings. Obviously, there are masonry walls, which I said could be done using bricks, but also other units, concrete blocks or AAC blocks, whatever is used. And then you can see these confining elements, which are placed at various locations. And for those who are civil engineering students, maybe I can ask a question. Where do you see in reinforced concrete buildings that these elements would not be provided and they're here in a confined masonry building? Do you have any answer that what you see as a difference? Where, if this was RC frame, where it's very unlikely that you would see the frame elements, vertical elements such as columns? Well, I'll help you. You can see that there are these confining elements around openings. These are very important because each of these confined masonry walls is confined only if it has these elements on both sides of it. So if there was no confinement here and here, this wall wouldn't be confined. So that's as simple as that. That is the logic. So similarly, this wall on the left is confined because it has confining elements on both sides. So the area in between openings is obviously unconfined, but that is not relevant. What is important is to confine the walls. So construction practice involved, where has it, most of you haven't heard about confined masonry, and you're from India and maybe some other countries, let's say North America, US. This is not practiced there, but it has been practiced for the last 100 years in many high seismically prone areas of the world and countries. And it was first observed, reported in Italy after the 1908 Messina earthquake, which killed about 70,000 people. However, they found some buildings that were standing, and they happened to be confined masonry. So it was actually not designed by engineers. It came from construction practice, and it proved it was tested by earthquakes. That's the best test, actually. And somehow, in 1930s, 1940s, this construction was then found in Latin America, in countries like Mexico, and then subsequently in Chile, Colombia, Peru, like many Latin American countries have confined, most actually. And maybe it was imported from Europe because there are lots of immigrants from Italy in Latin America. Nobody knows how that happened, but because there was no internet, there was no communication, there were no engineering conferences, and actually, as I said, it was not by engineers. So anyways, again, in Chile, it was exposed to a very significant earthquake in 1928, I think, and it performed again well. So that's how it started in Latin America. And but in those countries, they were very prompt in coming up with at least some general guidelines for planning. So since 1940s, 1950s, they had some either guidelines or codes which were written and gave some basic rules of confined masonry construction. And ever since that time, this construction has been practiced in those countries, as well as in some other part of the world, as this is framed, showing Mediterranean Europe. For example, I'm from former Yugoslavia. In my country, it has been practiced since part where I live is called Serbia, but it has been practiced since 1970s, and so it's in Italy, obviously, and some other countries, but not in the whole of Europe, I must say. And but it has also been practiced in Middle East, Iran. I don't know, for at least maybe 30 years. It has been exposed to earthquakes. They have some code provisions, I believe. Then in Indonesia, for 30 years at least, they don't have a code. And China. China has quite a few applications. In fact, very recently I received some photographs of confined masonry under construction in China. In China, it is a part of the code. So basically, how did it started in India? Like we are sitting here, and as I will explain, major portion of the campus, if it to speak, I'm not sure, like area-wise, is built in confined masonry. But how did it start? Actually, in 2001, there was a Burj earthquake, which was a very significant earthquake, and it revealed the very weakness of reinforced concrete construction in case it was not, frame construction was not designed or construction was not supervised properly. So obviously, and not only in India, in many other parts of the world, that is being actually a major killer of people in apartment buildings. And especially it's dangerous because apartment buildings have population, have lots of occupants. The taller they go, they have more occupants. So with the collapse of one building, automatically 200 people could die or so, or more. So anyways, so Professor Sudhir Jain, who happens to be director of IIT Gandhinagar, in 2005, I believe in my recollection, it's the first mention of some strategic thinking. He published an article in the Current Science where it was mentioned that confined masonry could be an option for safer construction in India. Without any, it was just not, it was just like, what could we do better to make it, the construction, this environment safer, the country safer. And after that, and actually about that time, in 2005, I was in India at IIT Kanpur under some program which was called NPEEE, National Program for Earthquake Engineering Education. I was invited to be like a scholar in residence, and Professor Jain was there. At that time he was a professor, program head probably, and he invited me, he asked me to write a publication on basics of confined masonry, which would be useful for Indian audience. So I wrote that. It was published by National Information Center for Earthquake Engineering, NICE, which is based at IIT Kanpur. In 2007, it was first published, and in 2008, and then right now we are working on a new edition, which will be published this year. So it was a basics, and that was the first publication, I would say, on confined masonry, very, very basic, very fundamental, without any engineering guidelines, how to design, but more of how does it behave, what is the performance past earthquakes, what are some construction rules, what are some basic design rules, and so on. So subsequently, a colleague from Switzerland, Tom Schacker, also published through the same center, he's an architect, so it's basic construction guideline. And subsequently, there were research studies started at IIT Kanpur, which has very good experimental facilities, and Professor Durgesh Rai, then CBRI Roorkee, and then, of course, IIT-GN, which I'm going to talk about. So everything started after that. Around the same time, in 2008, we have had a big meeting at IIT Kanpur, and formed something that is called Confined Masonry Network with people from 15 countries. It is a global network of researchers and professionals that are interested in confined masonry, and it is hosted by ERI, Earthquake Engineering Research Institute, based in California, but with strong participation of NICE. I'm the chair of that network as well, and have been involved and have co-chaired it since the beginning. So anyways, that was the idea was a global initiative to improve safety of buildings in the countries where the concrete construction is prevalent, and to introduce confined masonry. And how to do that, you will see an example of IIT Gandhinagar, which has done its own initiative, but it is through publications, through building capacity of all stakeholders, including architects, engineers, and so on. So through publications, through translating practices, transferring knowledge from one part of the world to the others. So because very often language is a barrier. When talking about Latin America, it is a region, as you may know, that most of it people speak Spanish, and most of the researchers publish in Spanish. Sometimes they can't, or they don't maybe mind translating into English and publishing in English, but lots of research has been done, except that people who don't speak Spanish are not aware of it. So anyways, this was all meant to be in English, and so this is that publication. It's available on NICE's website, Earthquake-Resistant Confined Masonry Construction, but I would suggest that you wait for a new edition maybe. It is, if you look at the NICE website, you will see these various publications. So let us move on. I would like to start by explaining the project, and then I explain the challenges, and then I explain the research. So, how confined masonry behaves. So, IIT Gandhinagar is located at, as you know, here in Palach village. It is on 400 acres of land, and which were taken over in August 2012. And construction started in June 2013 on completely bare land here, and the campus was occupied in July 2015. So construction was completed within 2 years of this first phase. So it is the first large-scale application of engineered confined masonry construction in India. This is a master plan of the campus, and you can see, maybe I can stand here for a moment. So we are here in academic blocks. This is academic area, these are hostels, and this is housing area here on this side next to the entrance. Actually, it's here right now. So this master plan shows some buildings that don't exist, because there are several phases of construction within a campus, and this is just the first phase that has been completed. So here is the housing, as I can show, where all faculty and staff lives. As you enter into a gate on the left side, that is the housing. And then obviously, I believe you know student hostels, because all of you stay there. So there's our hostels area. Here is Sabarmati River. And basically in this, the whole cast, and then last but not least, this is academic area, which I'm showing with the mouse. So in this campus, academic facilities, offices, lecture theaters, like the one where we sit, labs, are all made of reinforced concrete frames with masonry infills. So it is that traditional technology in India. And both student hostels and faculty staff housing are made of confined masonry. Maybe the first question, and I can answer it, why the whole campus was not built out of confined masonry? Because, see, for a theater like this, you have very large spans. It's large open space. Again, I'm speaking to civil engineering students, and you wouldn't be able to build confined masonry, to construct this in confined masonry. You need some other structural system. So confined masonry is really suitable for buildings like hostels, housing, schools potentially, but not these large areas. So this had to be done using some other system. Student hostels, I'll tell a little bit about them, and then later on I'll show you models of the hostels, done analysis models. So these are 6 hostels right now, 4-story buildings, or G+3, as said in India. Total built-up area of 36,000 square meters. And they have all complex plan shapes. If you look at the hostels, you can see that the plan shapes are all complex, like P shapes, C shapes, whatever you can call them, U-shaped. So they were in order for, again, civil or structural engineers know that at least for earthquake resistance, it's better to have regular buildings, simple buildings, rectangular, square. But of course, that's not reality. The needs of the architectural planning was that the hostels were irregular. So they were all divided, but it was possible, and it has been done, to divide them by so-called construction joints, vertical joints, like it is like cutting through the building at certain locations at the interface between these blocks, and make separate blocks. So for earthquake purposes, they will behave as different buildings. That was done with hostels as well as housing. So these are called seismic gaps when you talk about seismic design, and they should be wide enough so the two buildings, when two blocks are vibrating during earthquakes, they don't collide. So there is some rules about the width of that joint. So this is an example of a joint. This is one of the PG hostels, and I don't know, maybe some of you are staying in them, and you can see these joints are all over at this interface of the blocks. So these are the hostels under construction. Actually, one of them, I don't know which one. I took the photograph, but I don't know which one it is. And you can see these confining elements between the openings, that all these walls, exterior walls, are confined, and so many interior walls are confined. A particular challenge is with exterior walls because there are so many openings, there are so many windows, but that is how it was solved. I will say a little bit later why these bricks are gray as opposed to red. For those of you, and these are called hostels when they were plastered but not painted. So this is how they look after. So as you can see, after they're painted or plastered, you can't see that it is confined masonry. It was possible to see only during construction. In terms of housing, again, there are 30 G+2 or 3-story buildings. And they're housing up to, I think, 270 apartments. They're not all occupied right now. And the footprint area is 51,000 square meters. There are 3 types of housing, depending on the 3 types of apartments in terms of size. And they range, area ranges from 108 square meters to 256 square meters. So they're pretty large apartments, very spacious. And you can see before the construction, architects made some models, and that's how these housing blocks look like. So you can see here at the left side, at the bottom left side, you can see one housing block. So it's also divided by the joints into 3 parts. Because you have this narrow part, so the joints are here, and they're separating the blocks into three parts also to make it regular, because there is a staircase here and some concerns for seismic behavior. So that's what was done for the housing as well, as opposed to hostels. So here is, you can see exactly the plan of a block as I was showing. So this is locations of the joints. This is basically one apartment along the 3 floors. This is plan area. And that's how they were done. So this is housing under construction. You can see again lots of openings, there are lots of balconies and all that. So confining elements are maybe not so visible because it's all gray, because the bricks were also gray shaded or gray colored, but they were confining elements practically at all openings there. And this is after plastering, where you cannot see any more confining elements. So what were the key features of, and also challenges for confined masonry in campus construction? Obviously, I said that these key elements are these reinforced concrete confining elements. Vertical elements are called tie columns. So in reinforced concrete frame construction, we call them just columns. Here we call them tie columns, and I will explain why, because they actually don't work like columns. As I was saying, this is just reinforcing for masonry, just to make it different. And horizontal elements at each floor level, they're called tie beams. So you remember I was showing framed, confined in 3 places. So on the top is tie beam, and these 2 are tie columns. So each confined masonry wall is confined by two tie columns and 1 tie beam. So we'll talk about these various features. So starting for this, what you have seen, just to review. So we start from the plinth level. This is called plinth band. And then there is wall construction. There is this reinforcing in the tie column sticking out, as you will see, and then there is a construction of these concrete elements. Just a couple of words about materials that were used, masonry materials. As you know, in most of the world, even nowadays, and from olden times, from ancient times, clay bricks, red bricks were used, whether they were burnt, these are burnt in kilns or some other facilities, or unburnt, which in this case they're sun-dried or adobe. Mostly in India nowadays, these red bricks are used, burned clay bricks. But in many areas there is a shortage of bricks or shortage of good quality, good strength bricks. And in that case, the fly ash bricks are used. So they're gray in color. They're made of reinforced of concrete. But they are just fly ash, and they use fly ash, which is a byproduct of thermal plants. So they're environmentally friendly. They're positive. It's positive to use fly ash in concrete construction. And when the campus construction started, there was a conclusion was made after some research that there are no good bricks in sufficient numbers available in the area. And the demand was to use 100,000 or 1 lakh, for Indians, bricks per day, which is a significant amount. So it was not available, and also strength of the bricks that were available was not good. So that's why fly ash bricks were used. The required strength was 9 MPa. They actually compressive strength. It is when you crush a brick that you get divide the force by the area, you get 9 megapascals. That is a minimum strength. They achieved many more megapascals. Actually, they were much stronger. Whereas clay bricks were used under for underground parts, which means foundations. So, fly ash brick manufacturing plant was set up at the site to meet the needs of the campus construction, and it was going on for the whole 2 years or more. So capacity is 65,000 bricks per day, so some had to be procured by externally, but most of them were obtained from the campus. Also, there was a controlled testing facility for checking the quality of bricks and so on. And fly ash is available from local thermal plants. As you could see, there are several thermal plants in the vicinity. So fly ash brick manufacturing plant is here. These are some examples. And these are workers carrying the bricks. You can see them. And this is now some construction. So this is the horizontal elements are plinth beams. And you can see vertical reinforcement sticking out of them at the plinth level. Then you can see this vertical reinforcement again when the plinth concrete was constructed. So this is how the site looked like. Lots of vertical bars sticking out. So these are walls. These are the vertical tie columns. And then this is a formwork on the right-hand side for tie columns. So if you look at the corner, formwork had to be provided on 2 sides, whereas in reinforced concrete frame construction, you would have formwork on 4 sides. So there is some savings on the formwork, but at the same time, this was a challenge, how to connect formwork, how to support it in the situation where it was first application in India. And the experience with this type of even formwork support was not there. So it's all explained in the publication, which I'll share with you to take home and read. But a few photographs. These are how formwork was applied for horizontal concrete elements. This is a slab construction on the right-hand side. And this is when I first visited the site, actually in April 2013. That is how it looked like. And this is a photo I actually took, and then this is in September 2013, already looked different with the construction at the plinth level being done. And July 2014, about half of the housing was, or hostel, 60%, more than half of the construction was completed in hostels and housing areas. And here in July 2015, first students moved in. The first lectures were given in this campus. Some faculty moved in. Most faculty moved in early in 2016, though. So this project won several awards, including the HUDCO, that is Housing Development Corporation of India Award in 2015 for cost-effective rural and urban housing, including disaster-resistant housing, to acknowledge the first application of a new technology in India, and won some other awards for different features of the campus. In fact,
at this point, I would like to say that it would be really highly recommended that you get a lecture on, say, green features of the campus and what they are and how it was built, and maybe visit them. It's really unique, will be a unique opportunity for many of you. So here is Professor Jain, director of IIT-GN, and he was standing in the old campus, which was temporary in Chankeda, here also in Ahmedabad. And he had a hard time, even though he had the idea of implementing this, he had a hard time of explaining to anybody what is confined masonry. So what he decided to organize building a small confined masonry wall. You can see him showing tie column, and these are brick masonry, and then showing there were different types of connections here. So it was a challenge for engineers working. The project was implemented by CPWD engineers, Public Works Department of India, and they had never heard about confined masonry. For architects, their main design engineers, same thing. All they knew is about frame construction. And obviously construction workers, then they would not have heard if they have not, they're certainly not reading books, but even they have not seen it anywhere. So anyways, little by little, with as Professor Manish Kumar mentioned, with some internal and external input, the learning curve was, had to be relatively steep, because the construction had to be done within a tight time frame, as you could see, of 2 years, which is for Indian standards very fast. And so learning was there, and the lessons learned from this construction have been actually presented in the publication, which you will be able to get a copy of, free copy, which is actually explaining construction and key challenges. And it is a good publication. You can maybe either circulate now or at the end of they can pick, if it is possible. This is a complimentary copy for each of you. It's one of the IIT-GN publications. In fact, IIT-GN has decided to document all construction on campus of these nice features in different publications. This is the first one, and it is on confined masonry. I'm a co-author, one of the lead authors on the publication. So in order, besides these construction features, I didn't go much into these challenges, but if you are especially a civil engineer, even if you're not, it's good to read it. It's not written in a language that is too sophisticated, or it should be clear to everybody, and explains, of course, first what is confined masonry and all that. But it gives lots of photos from construction, and the key challenges are highlighted. So research at IIT-GN. About the same time when the campus construction was still going on, and that was all happening in the temporary campus, I've been invited to to work as a visiting professor, giving lectures for 1 semester, depending on my availability. And so in 2014, I first offered the course on analysis and design of masonry buildings for graduate students, PG students at IIT-GN. It is called C613. So in which confined masonry was pretty much a significant portion of the course, besides reinforced masonry. So it was mostly talking about modern masonry construction, not old or rural construction, how to build really good, decent buildings in confined masonry in India, and in reinforced masonry also. And as a result of this course, some students showed interest to do research, to do their thesis on confined masonry. Some were working under guidance of course, other faculty members, Professor Diman Basu, and I also supervised or co-supervised some of the students. So far, 3 students have done research here at IIT-GN, and theses have been completed. So this research is necessary to gain a confidence in new technology. It's very difficult to convince people just because you are expert and you say, take my word, and in Italy they're doing it. But saying, yes, but we are in India, let's see how this technology behaves in India. So at IIT-GN, there are not yet experimental facility to test confined masonry walls. So experimental research was done independently at IIT Kanpur, which has been well established, old IIT, and they have good experimental facilities. So Professor Durgesh Rai and his students, there were several master's and PhD theses on confined masonry. and analytical research was done here. So just to get an idea for those of you who are not even civil engineers, not even, of course, you're not civil engineers, so you're not doing this kind of modeling in this way, that's what I want to say. So for us civil engineers, the most challenging part is how to translate an actual building with this bricks and mortar into a model. This was a hostel, this is a plan of a hostel. How do we get from there to here? So a part of the training for the students, this is an analytical model of the building which could be subjected to simulated earthquake or to some just pushing static loads, depending on what kind of analysis you want. So this is done in software SAP 2000, and there are many other software packages that can do that. And so students were doing modeling. In fact, students in the first group had to do analysis of their own on one of the hostels. And so they had to do design in groups of the hostel in confined masonry and also in reinforced masonry, using that software. And they basically were separated in groups, so each group was doing one of these blocks. We had 4 groups. So what model they used, just to get an idea now what am I talking about? So one simple approach, but it seems works for most applications or most practical purposes, is so-called wide column model. That is when we take an actual confined masonry wall, let's say along one side of the building, and so this is one wall, this is the other, this is the third one. So each of these walls is modeled as a column, as a wide column. Let's say it is 3-meter walls, but you may model it as a linear element. And then, so is the second, so is the third. And then these horizontal elements are representing floor slabs, floor or roof slab. And then the reason these blue lines are so thick, these are so-called rigid elements. So these are hypothetical elements that simulate the stiffness of the wall, or the interaction between the wall and the floor at those levels. So model has some intricacies, obviously, and then these elements here are simulating this area below the parapets, below the opening. So anyways, that is the concept. And some students have done that, starting from simple models like this. Kiran Rangwani is one of them. I mentioned her name, I think, on the next slide. So she did MTech in 2016, and she was comparing finite element models with these wide column models for walls with solid walls as well as walls with openings. So she was doing lots of different studies and showed that it works rather well. She was comparing. So we compare these structures in terms of the stresses or forces that are internal into these walls due to applied loading, and then displacements, how much does it sway, using different modeling approaches. And we compare it with the experimental data as well. So that is what she did. Another interesting approach is equivalent truss model, which again 2 students did. One was under Kunal Gaisas in 2015 under supervision of Professor Basu. And Nikita Rankavat last year, I co-supervised her. And so the other model is, so there is no one solution for many civil engineering problems. So one way is to model it as a wide column. The other way is to model it as a strut and tie. Because these concrete elements are the main benefits of concrete are actually reinforcement of reinforced concrete. So we take these benefits and we model this as ties or struts. And then masonry is always in compression because masonry can work only in compression, so it is a strut. And one feature that I should mention here, one advantage of confined masonry, which is simulated by this black dot, is that we actually don't expect to have any moments, bending moments transferred through these connections. Therefore, it is a very flexible connection compared to moment frames. So therefore, it needs less attention and is less demanding than construction of frames. And that is one reason for higher seismic safety of confined masonry, because it's simpler. It's easier to achieve in practice without high level of supervision. So anyways, this is experimental studies done in Mexico showing these strut mechanisms. And so Nikita, who did the research in 2015 and 16, she was actually using some experiments from IIT Kanpur and was comparing her model. She did that strut and tie or equivalent truss model. These are alternative names. and she was doing with 1 strat or 2 strats, and she was modeling nonlinear behavior. Even after the masonry cracks, after concrete cracks, what happens? So it's a very complex model, and it's appropriate for definitely graduate studies. So, and then she was getting, let's say this green line is, red line is experiment, and then she was trying to compare her results with experiment. This is just to illustrate the process. Anyways, in some cases she got good comparison, in some cases she got worse, but she was trying to explain why it happened, why there was good in some cases and some other it was not. So in other countries, there were lots of experimental research. Like I mentioned, Mexico is one of the first countries that used confined masonry. They're confident in confined masonry because they did extensive studies for 50 or 60 years. This is, for example, 3-story confined masonry buildings, which they subjected to shaking at the shaking table. These are facilities that simulate earthquake. So you can, let's say if there was a record of Burj earthquake, you can use Burj earthquake record or any other earthquake in India, and you can shake the building to this. So you can see here, I don't know if this is going to work, hopefully yes. This is a simulation that is from that Mexican testing. So you can see that building is damaged. So I want to say this. We as civil engineers, structural engineers, don't expect, and our codes don't expect our buildings to be undamaged after a major earthquake. We want people to be alive, to walk out alive of those buildings. Life safety is the criteria. So this building is badly damaged, but it didn't collapse under even very high. This was a pretty significant shaking. You can see significant damage at the ground floor level, and that is expected for this type of buildings. Moving on, what is the framework? What does it take to actually implement? This is one project, but how many more projects are going to be there in India and when? So what does it take to get from here to large number of projects? Well, the critical things include development of educational resources, training and dissemination of results, to involve key stakeholders in the construction industry who will be implementing this technology, architects, engineers, and developers, builders, to have resources at all these levels, and training. And IIT faculty and students, to scale that IIT has the capacity, are certainly involved in this process, but it requires a larger involvement of engineering community in India to make it happen. And right now at IIT there are 2 courses that cover design of confined masonry buildings at IIT both, one is at undergraduate level, the other is at graduate level, UG and PG. And a few short courses have been offered, one 5-day course in 2014 for external audience, and also one course was just offered last week with some external participation of students. And a short course for architectural students was delivered last year at CEPT University in India, in Ahmedabad. So, as you have received this publication 2015, so lessons learned from this project were summarized in the publication that you have in your hands, and it's also available electronically on the IIT website if you will prefer to have a soft copy. So, resources that have been developed as a result of this campus construction and research done in India. The team of academics, I was a part of it, and Professor Durgesh Rai, who did significant research in Kanpur, and some others, have proposed a new Indian code, Indian standard for confined masonry, which is now under consideration. We are also working on preparing design handbook for engineers with examples, with explanation of all the principles for design and analysis of confined masonry buildings. And also at the same time, we are updating a publication that I mentioned. It was first publication in India for adapting it for architects so that it's very clear for them how to use confined masonry. This will be released by NICE in 2017 this year. And again, IIT faculty and students have been involved in developing these resources. Hopefully the handbook will be also done by next year. So conclusions, research, both fundamental and applied, is needed, is essential for introducing a new technology in any country, in any environment. Research results must be disseminated among key stakeholders. Otherwise, if you sit in your lab and do very nice research, that's nice, but this is only part of research. Educational resources and training are an important aspect of this research dissemination process. So researchers have to be good communicators. Besides being good researchers and having quality of researchers such as curiosity, background, of course, that goes without saying, perseverance, and but the ability to communicate both for scientific and less scientific audiences is critical. In fact, any studies show that research papers done, published in journals are read by least audience. Most audience is outside those journals. However, of course, research process is such that we do publish in journals and conferences and all that. So these are conclusions. Thank you. This is the first group of students that was trained in confined masonry. They were PG students in 2014, and we visited this site. That was a site visit, field visit. We took a trip, school bus from Čankeda to come and see this campus under construction. So from there to here, it's been 3 years, but lots of things have happened, and this is a story about how this happened at IIT GN, and hope that some of you maybe take it up for applications, other applications in India or research to start with. So thank you very much.
Any questions? Yes?
Ma'am, as you said that this technology is good for lateral loading, as in earthquakes and seismic design. So, but for the vertical loading, as you said, the compressive strength of bricks was around 9